In this presentation, we're going to look at the normal distribution, or a question related to the normal distribution. Paget's disease is estimated to affect 10%, that's important for later, 10% of people over the age of 65. Okay? It is known that amongst people over the age of 65, over 65, without the disease, that's to say non-sufferers or people without the disease, some blood measure X in suitable units is normally distributed with a mean of 7 and a standard deviation, or a variance of 9, which is a standard deviation of 3. So variance of 9. Okay. But for people over 65 with the disease, suffering from the disease, it is a mean of 19 and a standard deviation, or a variance of 36, which is to say a standard deviation of 6. Okay. A value of x greater than or equal to 10 is taken as a cause for further investigation. So what proportion of non-sufferers, so we're just looking at that first group there, non-sufferers, will be investigated. So this is a sort of straightforward enough one to get us started. For a non-sufferer, x is normally distributed with a mean of 7 and a variance of 9. Okay, so that's what we actually have to find out. Probability of x greater than or equal to 10. What we do there is calculate the z-score, okay, and that is 10 minus 7 over 3. Just to be clear, this is the formula for calculating a z-score, and here we use the variance, the standard deviation, which is the square root of the variance. Okay, so this is that is the variance there, and we get the square root of that to get our standard deviation, which we use in the formula. So anyway, we end up with a z-score of 1. So the probability of x greater than or equal to 10 is equal to the probability of z being greater than or equal to 1. Here we use tables or some such mechanism to find that. Okay. So the probability of x greater than or equal to 10 is 1 minus the probability of x less than or equal to 10. Okay, a little bit of a fudge there with regard to using those symbols as complements of each other. It's not strictly true, but it's so mathematically close it's indistinguishable. And essentially what we're doing here is we're finding this value here, probably z less than or equal to 1. That is 1 minus 0.8413, and that gives us a probability of 0.1587. So just actually, if you're wondering how I got that particular value there, that was from statistical tables. And actually, I use multiple different approaches in my videos for calculating these values here. So I'm actually using one particular approach here, the cumulative distribution function. Okay, and that is phi of 1, the cumulative distribution function for the z normal distribution. So you can actually use it finding the R programming language as well, p norm. Sorry, I'll leave that there for another time. That's a bit of digression. I'm going too far off. Anyway, the answer is 0.1587. Okay. So the next question is, what percentage of sufferers over the age of 65 will go undiagnosed? Okay. So what proportion of sufferers so essentially, what is the probability of x less than or equal to 10 here, or less than 10? Okay. This actually is a very simple question. So remember, the check is they won't be detected if the threshold is under a particular value 10. Okay, so we're using the same approach here. The mean now is 19 and the variance is 36, which is to say the mean is 19 and the standard deviation is 6. We're calculating pretty much the same type of calculation here. We're calculating a z-score for x is equal to 10. Okay, but what we're interested in here now is probability of x less than or equal to 10. I should really write that as a capital letter there. X less than 10. Okay, and that is equal to the probability of z be less than minus 1.50. And again, that is statistical tables work there. Okay. So the cumulative distribution function of minus 1.5. Essentially, this is using tables to do this. Okay, so which I'm not going to get into in this video. The answer we get, though, is 0.0668. So 6.68%, nearly halfway between 6% and 7%, which is actually quite a lot. So, part C. At what critical level x instead of 10, so we're going to use some other value other than x, would the false positive rate be 5%? Now, that's quite chunky, so to sort of get your head around it. So, what we were looking for is some value of x such that only 5% of non-sufferers will be above this level. Okay? So again, false positive rate. That means the people that you detect or you're looking out for, but they don't have it. So the false positive rate means the non-sufferers. Okay, that's important. It's trying to sort of digest what's going on here, because you might not be given a tip like that. You might not be given it to you as easy as this. Okay? So essentially what we're looking for is some critical level here, x or x0. Okay? And what we want is the probability of x being greater than this threshold, given that we're dealing with non-sufferers, okay, to be 5%. Okay. So this is familiarity with the normal distribution comes into play here. Okay, so essentially what we want to know is what is the z-score that corresponds to an upper tail of 5%. And that value there is 1.645. And this is actually quite important to know where that comes from. I'm not going to do it in this question actually in great detail. But just to sort of say, probability of z being greater than or 1.645 equals 0.05, okay, and probably less than that, or less than or equal to 1.645 is 95%. This is a number that you're probably going to see quite a lot of, 1.645. Anyway, let's rub that out. So essentially what we have here is we have 1.645 here, okay, and we're going to use our z-score formula to actually work backwards what the corresponding value of x is. Okay. Now remember, we are dealing with non-sufferers, so our mean is 7 and our standard deviation is 3. So essentially what we do is this expression here, we rearrange it algebraically to isolate x or xo. The O is actually just to sort of specify it as a particular value of x. Okay, so when we rearrange that algebraically, we get a new value of, or work it out as 11.935. Okay, so essentially only 5% of non-sufferers have some blood factor level in excess of 11.935. So moving on to part D, it's a little bit smaller here. If all people over 65 are screened using the threshold of x greater than or equal to 10 as a criterion for further investigation, what proportion of people would be investigated? Now this is all people. This is sufferers and non-sufferers here. Okay. Now, what is the breakdown of each? Well, we know that there is 10% with the disease and 90% without the disease. We actually were told that at the start of the question. I pointed it out, the 10%. So this is 0.10 and this is 0.90. Okay. So the probability x greater than or equal to 10, given you're a sufferer, is the complement of this value that we found earlier on. This is from part 2, part B. Okay. That was the complement of that. But that value there is 1 minus 0.0668, where 0.0668 is what we found out. This is what we found out in part A. That comes from part A. Okay, so working all this out together, and I'm just going to speed things up here and say that is should work out to be 23.62%, 0.2362. So finally, if either of those who get investigated, what is the proportion of individuals who actually have the disease? So the probability of having the disease, given that x is greater than or equal to 10, okay? So the proportion that does have the disease is that there, probability of x greater than or equal to 10, or sorry, that would be flagged, is x for having the disease. Not that they do have it, but that they're investigated for it. X greater than or equal to 10 is 23.62%, which we just found previously. Okay, and this is the probability of having the disease and no, this is probably greater than 10 given that you have the disease. Essentially what we're doing here, so I'm just being mouthy here, so we're just using this value here. Okay, so this actually corresponds to this expression here. Again, probability of x greater than or equal to 10 given that you suffer times the fact that you're a sufferer. Okay, so that is what we're using there. This is what that value comes from. Okay, this is conditional probability. The conditional probability formula there. So I've just sort of running out of breath and running out of time there, but it's essentially just an extension of part D, this part, just reworking the part D with Bayes' theorem. So we'll leave it there.